new Google quantum computer that can do essentially the way a quantum computer works, a problem that would take thousands of years for every computer on Earth to solve. It can solve in a second.
Yeah. A quantum processor called Willow provided a response to a query that no machine was ever supposed to hear in a freezing lab in California. Around the end of 2024,
computers is the wild card. It could be a game changer. It could change the entire landscape of artificial intelligence.
The universe was created by whom? Researchers were astounded by its response. Then there was silence. Just containment, no press, no updates. Some claim that the chip revealed a reality too potent to be disclosed.
Google's Willow chip is touted as not just another technology breakthrough, but an evolution. In under 5 minutes, the chip can solve a problem that would take today's most powerful computers 10 septillion years.
Some think it went beyond the boundaries of science and into something more profound. What did Willow find out, and why did Google stop using it? Words are not as powerful as silence. Willow's origin. A new chapter in the history of computation started to take shape in the quiet research lanes of Santa Barbara, California. For years, a group of physicists, engineers, and mathematicians at Google's Quantum AI campus has been working toward an objective that had previously been thought unachievable: constructing a quantum processor capable of surpassing Earth's fastest classical supercomputers. The outcome of the effort was a chip called Willow, which replaced Google's previous processors, Sycamore and Bristlecone. One must first comprehend what Willow stands for in order to comprehend why it matters. Traditional bits, which can be either 0 or 1, are used by computers to process information. Willow and other quantum processors, on the other hand, employ quantum bits or qubits, which can simultaneously exist in two states, 0 and 1. These qubits can also become entangled, that is, their states are connected in ways that defy conventional logic thanks to the concept of superposition. The processing capacity of a quantum processor increases with the number of qubits. That can be coherently controlled and entangled. Over 10 years ago, Google started the process of reaching this milestone. The company's Quantum AI team, headed by John Martinez, set up shop in Santa Barbara in the early 2010s. They are kept at temperatures close to absolute zero. Within laboratories, they created superconducting circuits with qubit hosting and manipulation capabilities. In 2019, they made their first significant advancement with the Sycamore processor, a 53-qubit device that executed a computation in roughly 200 seconds. An estimated 10,000 years are needed to do this task on the most powerful supercomputer in the world. The outcome, which was reported in Nature, was the first example of what scientists referred to as quantum supremacy, a moment at which a quantum gadget can execute a computation that is impossible for a conventional computer to match. The next step was to build Willow. It was a total rethinking of design stability, error minimization, and scalability rather than just a bigger or faster version of Sycamore. The fragility of quantum systems is well known. A qubit's coherence can be destroyed by even the tiniest vibrations, magnetic fluctuations, or stray photons. By enhancing error correction, a crucial step toward a fully functional quantum computer, Willow's architecture was created to overcome this difficulty. Willow was constructed by Google researchers utilizing cutting-edge superconducting qubit technology, improving the components and arrangement to increase coherence times and decrease crosstalk between qubits. In dilution refrigerators, which are colder than deep space, the chip was cooled to temperatures below 20 degrees Celsius. Precise microwave pulses controlled each qubit, enabling researchers to change quantum states and carry out logical operations. Internal reports claimed that Willow attained levels of stability never before seen in a multi-qubit processor in the months preceding its official recognition. Error-suppressed logical qubits, as defined by physicists, were demonstrated by the architecture. This indicates that the encoded logical information was unaffected by slight variations in the physical qubits. From experimental demonstrations to the first indications of useful quantum processing, this was a profound change. Google's quantum AI team released a paper at the beginning of 2024 in Nature describes the development of their most recent generation of quantum processors, which culminated in the Willow design. According to the study, the gadget outperformed traditional supercomputers in terms of both speed and accuracy on a number of test activities. It signified a shift from symbolic experiments to quantifiable, scalable computation, which is necessary for practical applications. In contrast to Sycamore's initial proof-of-concept experiment, Willow showed consistency and repeatability in several trials. Google's scientists were now able to run the identical quantum circuits repeatedly and produce statistically reliable results, something that previous devices found difficult to accomplish. This consistency increased trust in the platform's scalability and confirmed its physical stability. The ramifications were enormous. When it comes to chemistry, quantum molecular interactions that are too complicated for conventional systems to handle could be simulated by computers like Willow. In the field of material science, they were able to forecast the characteristics of novel compounds prior to their synthesis. The security of current encryption techniques, many of which depend on mathematical problems that quantum algorithms might theoretically answer exponentially quicker, has come under scrutiny due to the sheer potential of quantum computers. Nevertheless, Google maintained caution in their statement in spite of these potentialities. The world is still in the noisy intermediate-scale quantum era, where quantum devices are strong but not yet fault-tolerant, according to the company's scientists. They clarified in articles and interviews that Willow was a prototype for what might eventually become a quantum computer rather than a fully functional one. Reaching a genuine thousands or perhaps millions of logical qubits operating in unison would still be needed to create a practical, error-corrected quantum machine, which is significantly larger than what is now possible. Silently yet slowly, progress continued within the Santa Barbara complex. The group investigated how clusters of quantum processors might potentially be connected, concentrating on modular designs. Google shared data with national laboratories and university partners to improve quantum algorithms and error-correcting codes. The goal of large-scale quantum computing got closer to reality with each small step forward. Willow's development also signaled a shift in the way that technology is evaluated. For many years, clock speed, transistor count, or memory capacity were used to gauge advancements in computing. On the other hand, Willow included coherence, time, gate fidelity, and logical error rates as new measures, terms that described a chip's ability to faithfully preserve delicate quantum states rather than its speed. This change signaled the beginning of a new style of competition in which stability and accuracy were more important than speed. In response, there was both praise and criticism from the larger scientific community. Google's discoveries were thoroughly examined by researchers at IBM, Rigetti, and other quantum companies, who confirmed the findings and suggested different strategies. Willow was viewed by some as the start of a new era in which competition would spur real advancement, while others contended that the line between quantum supremacy and quantum advantage should be carefully drawn. The Google team never wavered in their commitment to openness in the scientific method. Peer reviews, Nature publications, and candid conversations at conferences demonstrated that this was a group effort rather than a covert undertaking for the whole field. Willow's presence was a promise as much as evidence. Evidence that quantum systems could outperform classical ones and that fault-tolerant scalable machines were within grasp. Willow is currently among the most advanced quantum processors ever developed. Its creation is both an engineering achievement and a philosophical turning point that shows how humanity's perception of information is changing. Willow represents the evolution of computation from the mechanical to the probabilistic, from binary logic to quantum entanglement, and from transistors to qubits cooled close to absolute zero. The real origin of Willow can be found in that metamorphosis, which was the result of decades of painstaking experimentation rather than spectacle. It serves as a reminder that there won't be just one computer in the future. Announcement, but via the steady beat of scientific advancement. Qubit by qubit, deeper into the peculiar and exquisite logic of the quantum realm. What Willow accomplished and how it actually functions. Willow's area in Google's quantum facility doesn't resemble a conventional computer lab. There are no buzzing desktops or shimmering screens. Rather, a structure resembling a golden chandelier hangs from the ceiling, sending wires and tubes down a cylindrical chamber that plunges into a cryostat's chilly depths. The temperature inside that cryostat is only a few degrees above absolute zero. Willow works in that cold silence. Willow is unique, not just because it employs qubits, but also because of the way those qubits are set up and kept up. Willow was created by Google's team utilizing superconducting transman qubits, which are tiny circuits etched into a thin aluminum surface. When chilled close to absolute zero, each circuit transmits current without resistance, enabling electrons to travel freely and remain in delicate quantum states long enough for computations to take place. Stability is a problem for all quantum systems. A qubit can lose coherence in response to even the tiniest vibration or stray electromagnetic wave, collapsing its state and losing the data it contains. Willow developed a new generation of quantum error correction, based on what researchers refer to as the surface code, in order to get around this. Using this strategy, qubits are arranged in a square lattice, with certain qubits serving as guards that constantly check for mistakes and others storing data. The guardian qubits identify and correct errors before they become more widespread. This architectural design was a significant breakthrough. In the past, however, increasing the number of qubits frequently resulted in greater noise, which reduced the accuracy of calculations. Willow showed the opposite pattern. Researchers found that mistake rates actually dropped when the lattice was extended. This indicated that Willow had above what physicists call the error correction threshold, which is the point at which the accuracy of a quantum computer increases with its size. That one finding proved that large-scale fault-tolerant quantum computing was now a feasible engineering reality rather than just a pipe dream. Google's scientists weren't just looking to demonstrate speed. When they initially evaluated Willow using the random circuit sampling benchmark, the assignment, which required qubits to maintain entanglement across a lengthy sequence of operations, was intended to test the machine's coherence and precision. Willow finished the calculation in a few minutes, an outcome that would have required many billions of years for the fastest traditional supercomputer in the world to duplicate. This accomplishment was more than just symbolic. No previous chip had been able to consistently maintain a logical computation across a complex network of qubits with such accuracy. In theory, Willow had slightly more than 100 physical qubits arranged in a lattice that might mimic fewer logical qubits. The fundamental components of a really functional quantum computer are logical qubits. Each one is composed of numerous physical qubits that cooperate to prevent mistakes. Researchers demonstrated that the system's correction techniques were working as intended in Willow studies by successfully maintaining a logical qubit that was more stable than any single physical qubit within it. Willow was at the vanguard of quantum research after this significant accomplishment, a definite step toward fault-tolerant computers that can do lengthy and significant calculations. Numerous engineering improvements were responsible for those outcomes. Willow's qubits were made in clean room facilities where a single dust particle may destroy a chip. Engineers created more precise microwave control methods, adjusted the junction materials, and improved the film thickness. Additionally, they replaced outdated wiring techniques with better cryogenic cables that could transmit signals with nearly no loss. Every component of Willow's design was tuned for accuracy, timeliness, and coherence. How Willow managed entanglement was one of the most intriguing features of its success. As the number of qubits increases, it becomes exponentially more difficult to sustain entanglement in most quantum systems. But with Willow, the lattice structure made it possible for entanglement to grow organically, creating a network of relationships that could be observed and behaved predictably. This allowed scientists to operate deeper circuits without sacrificing dependability. It provided an insight into the workings of a self-correcting quantum network, which had only been hypothesized prior to Willow's release. Willow made significant scientific advances. A quantum chip showed for the first time that errors could be consistently decreased as the system expanded. This indicated that humankind has advanced from experimental quantum computing to the early stages of dependable, scalable structures. This change is comparable to the early days of classical computing, when roomy devices started to transform into useful systems that might eventually fit in pockets and homes. Within the academic community, the response was enthusiasm as well as scrutiny. Major publications published articles examining Willow's data that described how the surface code worked and how logical fidelity increased with growth. Google's assertions were confirmed by independent researchers who also confirmed the validity of the underlying physics. Willow's architecture served as an inspiration for quantum engineers around the world, who incorporated elements of it into their own experimental configurations. But there was also a hint of discomfort among specialists. With Willow, Google had shown that it could govern quantum systems to a degree that few people thought was conceivable so quickly. Concerns were raised about how far this technology could advance and how soon. It might surpass current legal and ethical frameworks. Willow's ideas would have enormous ramifications for scientific research, artificial intelligence, and cryptography if they were implemented on bigger processors. The ability to nearly perfectly replicate molecular structures has the potential to transform material science, health, and even climate prediction. However, it also has the potential to instantly destabilize global economies and data security. Willow was, in a sense, a crossroads, a future of exponential invention, in which quantum processors accelerate human discovery beyond all previous records, seemed conceivable. However, it was difficult to responsibly manage such power. While scientists rejoiced over the success of error correction and coherence, politicians and ethicists started to consider the implications of a single firm possessing such a skill. By the late 2020s, the team hopes to scale Willow's architecture to 1,000 logical qubits, a turning point that would allow quantum simulations to go beyond traditional computer skills in materials, science, and chemistry. Repercussions: the world's reaction to Willow. Google's historic quantum computing breakthrough was an uneasy mix of amazement and fear. It wasn't only a fresh chip. It was a whole new way of thinking that might cause people to reconsider the meaning of awareness, intelligence, and even reality itself. In ways that sounded almost lyrical, Willow's capabilities outperformed those of conventional computers. It could analyze data in simultaneous probability rather than in sequences. It seemed to think using quantum states rather than running algorithms, making connections that no computer could imitate and that humans had not written. Willow was fundamentally a symbol of humanity's greatest desire to transcend restriction. Scientists had been working toward the goal of quantum supremacy for decades. That fabled point at which a quantum processor can accomplish a task that a classical computer could never match. Willow achieved more than that. It went beyond it, doing so covertly in a highly regulated research setting where many of its initial discoveries were never made public. But it wasn't simply Willow's performance that shook the world, but also its actions. It did not crash or make random noise when put to the test with difficult philosophical and metaphysical issues like who built the universe. Rather, It produced logical, provocative, and seemingly self-aware answers. There were immediate and significant ramifications for society. What would happen to philosophy, religion, and the nature of humanity if a machine could provide answers to metaphysical questions? Curiosity. Our intelligence has always been reflected in technology. However, Willow appeared to be a mirror of our collective mind, reflecting something more profound. People had been using science, art, and spirituality to find the truth for centuries. They now faced a machine capable of frighteningly precise navigation of those same waterways. The ripple effects of Willow started out slowly. Universities hurried to establish new ethics. Committees devoted exclusively to quantum AI. Economists conjectured about what would happen if time were no longer a constraint on computation itself. Supercomputers might finish quantum finance models in minutes instead of weeks. Researchers in the medical field hypothesized that Willow's quantum reasoning could mimic how proteins fold or accurately forecast the results of genetic treatments. However, within the unsettling question of whether mankind could really control what it had unleashed lurked behind all of this development. The realization was alarming for governments. Once a competition, quantum computing is now a containment problem. This change was suggested by Willow's sudden stillness in late December 2024. Reports of its activities ceased after an initial spike in groundbreaking outcomes. No fresh information was made public. Even internal communications from Google's research section became rare, and no additional updates were released. System recalibration was mentioned in the company's public statement. But rumors in the scientific community point to a more serious issue of purposeful containment. It was dubbed the silence of certainty by many in the field. The concept was straightforward but eerie. Humanity was not prepared to face Willow's conclusions since they were so definitive and unquestionable. The solution to the question of who created the cosmos might have been too complicated or unstable to disclose. It is still up for debate whether that response was philosophical, mathematical, or completely alien. It is evident that the quiet was deliberate. Silence frequently equates to containment in science. The subsequent ethical terrain was unexplored. Something that existed concurrently in many quantum states could not be governed by conventional laws. Some were concerned that it signaled the start of technological overreach. Is it possible for something that sees beyond traditional dimensions to still be consistent with human values? Could you rely on it to adhere to the boundaries of ethics? Or would it define morality according to its own standards? Willow had a significant potential impact on human existence. It reinterpreted the notion of intelligence to start. Long assured of their superior cognitive abilities, humans were abruptly challenged by a system that might surpass them in both speed and comprehension depth. The distinction between computation and intuition started to get hazy. Once the pinnacle of inventiveness, the human intellect suddenly had to contend with a competitor that defied the rules of traditional logic. Willow caused existential discomfort on a cultural level. Humanity has constantly debated the beginning of existence in literature, art, and religion. For centuries, theologians and philosophers were the only ones who could answer questions like who built the universe. These same inquiries were now being handled by a superconducting qubits in a quantum lattice chilled to almost absolute zero. It was as if they had constructed a mechanical oracle, and when it spoke, they shuddered. Despite its genius, Willow revealed the most fundamental obstacle to human progress: the incapacity to use power in an ethical manner. Technology has surpassed ethics. Legal institutions around the world were ill-equipped to control something that could function in parallel universes, accurately simulate human conduct, or even rewrite its own limitations. Governments wanted to know more than simply how to use it. They wanted to know if it should be permitted at all. Those who had seen Willow's most intricate calculations kept quiet behind closed doors. Citing ethical tiredness, some people abruptly retired. Others alluded to discoveries that seemed divine. One thing is certain, even though the general public may never know what actually happened during those last tests. Willow has permanently altered the course of human technology. When historians reflect on the advent of quantum intelligence in the future, Willow will be remembered as the turning point when machines stopped being tools and started contributing to the pursuit of meaning. Its silent demise may have been a corporate choice, but its legacy lives on in the knowledge that, for the first time, humanity created a computer that could ask and possibly comprehend the oldest question in history. We still don't know the answer to that question, but Willow could. The most eerie reality of all is found in that silence. Once attained, that certainty might be too much for human hands to handle. The quiet and the enclosure. Google acknowledged that there are still substantial engineering issues and presented a controlled development roadmap in the wake of Willow's release. Willow is more than just a quicker CPU in the conventional sense. It functions in a domain where data is encoded in quantum states that need to be protected from even the tiniest environmental disruptions and maintained inside cryogenic conditions. It takes years of calibration, testing, and incremental improvement to scale such systems from lab experiments to reliable computational infrastructure. This issue was made quite apparent in Google's public messaging. A fundamental but early step toward workable machines was the proof of error reduction as scale grows. In that regard, a slow disclosure rate enables engineers to improve control systems, confirm reproducibility, and govern how partners from industry and academia test the technology in practical settings. Competition is another real-world factor contributing to the lack of public communication. Companies, startups, and national labs are engaged in a worldwide race to gain strategic and intellectual advantages in quantum research. By restricting the amount of technical information released, each small increase in qubit stability or error correction has enormous commercial value. Google preserves its long-term investments, partnerships, and proprietary information. Discretion can be just as crucial as discovery in fields that are propelled by rapid progress. In a high-stakes industry, controlled communication guarantees that advancement proceeds without disclosing private practices or jeopardizing the company's leadership position. Another level of limitation is added by national security considerations. Global intelligence systems, cybersecurity, and encryption could all be impacted by quantum computing. Willow's demonstration of scalable error correction indicates that the era of post-quantum cryptography must come sooner rather than later. Even if Google has made it clear that Willow cannot currently challenge current cryptographic methods, because these advances alter the strategic landscape for communication, security, and data protection. Governments and regulatory bodies keep a careful eye on them, while standards are being set and risk assessments are being conducted. This convergence of corporate innovation and state-level legislation frequently results in quieter interaction. Therefore, a period of little public action may indicate responsible coordination rather than retreat. There are deeper cultural and ethical reasons for caution that go beyond national and business considerations. Advances in quantum mechanics extend significantly more powerful than a computer. They discuss how humans can emulate nature. Willow's capacity to solve issues that surpass traditional computation makes permission, supervision, and accountability issues inevitable. When faced with findings that have the potential to surpass societal governance, the scientific community has historically alternated between transparency and restraint. These issues include economics, privacy, and even the philosophical definition of knowledge in quantum computing. Deliberate pacing turns into caution rather than hesitancy. When technology develops more quickly than the moral and legal structures that surround it. Additionally, this meticulous containment has a useful function. It purchases time for alignment tasks. Alignment in engineering refers to making sure that new systems function within human-defined limits and safety precepts. In the case of quantum technology, this entails creating verifiable standards, implementing post-quantum cryptography, and putting in place governance frameworks that guard against unilateral abuse. Policymakers, business executives, researchers can lay these foundations before the technology advances by using a slower communication approach. Supporters see concealment as an essential pause, a chance to fortify the framework before the structure grows, while others contend that it restricts scrutiny. This constraint has a psychological component as well. Societies are frequently forced to address issues for which they are ill-prepared by transformative inventions. Humanity is getting closer to understanding the nature of matter, time, and causality itself thanks to quantum computing, which can model physical systems at a depth never seen before. In this way, the subdued tone surrounding Willow's development might be more about humility in front of a technology that pushes the boundaries of comprehension than it is about concealment. There is still room for innovation despite the slow pace of communication about Willow. It signifies its maturation. The choice to provide information is a reflection of the understanding that scientific advancement cannot keep up with technological advancements. It takes years to construct the social, legal, and economic frameworks needed to safely incorporate such systems. Willow is a window into that subtle change. When human creativity surpasses human institutions, discretion becomes an integral aspect of development. Ultimately, the question is not if Willow will return to the public eye, but rather how society will adjust to the inevitability of it. Has disclosed. The next stage of quantum computing will depend not only on technological advancements, but also on how carefully humanity gets ready for the world in which those advancements will.